Assalamu alaikum once again. We're back with another video lesson. In the previous video lesson, we were talking about lasers. We said lasers is simply, we can say light amplification by stimulated emission of radiation. That is simply what lasers are all about. Or you can say, of course, the amplification of light by stimulated emission of radiation. That is the same thing. That is basically a laser, and we all have seen lasers basically unidirectional. You can say a light beam that, of course, it spreads. I mean, it can transfer without spreading much. And of course, it has a lot of uses. And also it has a lot of differences, let's say, compared to an ordinary light, or just like the light that we have basically in our households, let's say. Okay, so, and also we said that lasers, basically, we have a laser source, of course, which is basically the device that produces the coherent light, or you can say produces the laser light, of course, at a single wavelength, you can say. And then after that, in the previous lesson, of course, we went through the comparison, or we did compare, let's say we went through the differences between laser light and ordinary light as well. But one of the main differences is this, you can say laser light is monochromatic, that is a single, you can say wavelength here, and it is, you can say it is coherent. That means they maintain the same or constant phase difference along the way here, which is unlike, let's say, light of a normal or ordinary sources here. So we have a few study tips before going to the next page here. Of course, lasers typically produce a narrow beam of coherent light. They are very narrow. They don't spread much. They don't disperse much, let's say. But in terms of, like, for example, transferring, of course, this is light. They can, for example, travel long. Depends on the energy of the laser, we can say. And then the second point, the waves emitted by a laser are in phase, basically. They do not shift relative to one another as the time progresses, you can say, because all the waves are in phase, and also they interfere constructively at all points. So one thing that is also very important, you can say, because all these waves are coherent here, they maintain the same phase difference, so they always, you can say, interfere constructively as long as we have the laser light. Because remember, for example, if we take a one wave or two waves here, let's say, now these two waves are coherent, they have the same phase difference. So of course, these two waves both at the same time, for example, they're above the equilibrium, they're below the equilibrium. So in either case, of course, you add them up, whether if it is above or below the equilibrium. So these are basically constructive interference, you can say, all the time. In terms of the intensity, you can say the intensity, the brightness of a laser light can be made much stronger. And of course, why? Because of this, let's say, coherent property that they have. Or you can say, which is much greater than that of incoherent light. So normally we know that the laser light are normally way stronger, you can say way more intense than just normal light waves here. Okay, now we have a few questions here. It says, one of them says, what properties does laser light have that are not found in the light that is used, let's say, used to light your home here? Okay, so now we said one of the properties, or two, let's say a few properties that we have is, we can say the laser light is coherent, and of course, and it is monochromatic as well. So, but the most important thing, we can have other lights that are monochromatic, one color, okay, but what makes the laser light to be so unique, so specific, is it is coherent. And we said that coherence basically the correlation between the phase difference, yeah? So they maintain a constant phase difference all the time. So this is what makes it so special compared to the normal light here. Now, another question that we have says, laser light is commonly used to demonstrate double-slit interference. Okay, why do we, or why should we use laser light to demonstrate double-slit interference? Why we cannot do that with light, for example, or why it would be best if we use laser compared to white light, or let's say normal light here. So why laser is preferable, let's say, to light from other sources of, let's say, for observing interference. We said earlier that because laser light is coherent and monochromatic, so of course it produces a clear, not just that, and also a stable interference pattern, unlike the blurred patterns from other light sources here. So what we can say, or we can summarize the answer to say this, if we use laser lights, we can get a clear, and of course, let's say, a clear and distinctive interference, while we cannot get the same result if we use the normal light, let's say. Okay, now another part of this is laser transforms energy into coherent light. So of course, we said lasers are very, you can say, unidirectional, you can say, of light, you can say. they have a high intensity, and also let's say they're coherent, yeah? But if they have high intensity, that means they have high energy. If that is the case, where do they get all their energy from? Well, the answer to that question is what comes next. We can say laser light comes from, or you can say a laser is basically, or if we follow this to a question, or with a question, we can say, what does a laser do to produce coherent light? That'll be the question. And then, of course, we can say a laser is a device that converts. So this is what it do to produce coherent light. It can, let's say, it can transfer light energy, it can transfer chemical energy, or it can transfer electrical energy, let's say, all to that into coherent light. So where does this coherent light comes from? It comes from this device converting, let's say, light energy, electrical energy, or chemical energy into coherent, you can say, light. That is basically where this coherent light comes from. So if you've ever been asked, that's one of the most important questions so far, by the way, yeah? Like, what do lasers do to produce coherent light? That's been in Uzari as well. Lasers normally convert light energy, let's say, or electrical energy, or could be even chemical energy. They convert that, for example, or one of these at least, into coherent light. This is where the coherent lights come from. Okay, all the light come from. Now, what do a laser use to produce coherent light here? Okay, so now another question is, what does the laser do now? Now, we've learned that these sort of, let's say, energies are converted into, let's say, coherent light, yeah? But what exactly lasers do to produce that coherent light? We'll say lasers use a substance called active medium, and this active medium, of course, could be liquid, solid, or even gas, let's say, to produce what? To which energy is added to produce a coherent light. So to make this one short, we can say normally lasers have a medium that is called active medium, a substance, let's say. The energy is added to that substance, and then this substance, of course, will give us as an output, let's say, for that energy, let's say, or as an output of that, let's say, and of course that output is basically a coherent light. So once again, all right, where does the coherent, or let's say, what do lasers do to produce that coherent light, or the coherent light? We will say lasers use a substance that is called active medium to produce what? To produce a coherent, to which energy is added to produce a coherent light. Okay, so now, of course, we're approaching to the work of the lasers. So basically, we're asking how lasers work, let's say. So now we know that lasers have a medium, it's called active medium, let's say. Energy is added to this active medium, and of course, this active medium as an output will give us this coherent light. Okay, now, what determines, by the way, so we said the active medium could be a solid, could be a liquid, or could be a gas here. What determines the wavelength of the light produced by the laser, yeah? So now, so far, we've been talking about this, but do we have, or do all the lasers have the same wavelength? The answer is no, okay? And of course, we have lasers of different colors as well, yeah? Different colors, that means different wavelength, you can say. So what makes, for example, or what gives us different, let's say, wavelength of the lasers, let's say? That'll be this question here. What determines the wavelength of the light produced by the laser, yeah? So why lasers, or the lasers we use, for example, they have different wavelength? That is because of this. The composition of the active medium, that is something very important you need to know, determines the wavelength of the light that is produced by the laser. So we can say why we have lasers that have different wavelength, let's say. That is because these lasers have different active medium, let's say. Okay, that will be one of the reasons, of course. So we will say the active medium of a laser, of course, that would give us different, let's say, wavelength for that laser. Or in a different word, you can say different active mediums will give us different wavelengths of laser light. Okay. Now, let's talk about the fundamental processes in laser light production. So what are the main process, or main, let's say, processes in, let's say, making laser light? We have three main processes, you can say, yeah? So what are these three main processes? And then, of course, after this, we're going to go through the detail of how lasers work, for example, but these are the three fundamental processes. Without these three, of course, we cannot have a laser. The first one is the absorption. And what do we mean by this? Of course, we have active medium. We said give light energy, electrical energy, or chemical energy to that active medium. So what do they do to this energy? Of course, they absorb that energy. Then after that, there was spontaneous emission. Yeah, this spontaneous emission, when, for example, you've studied that as well. When, let's say, an atom, let's say absorbs energy, it goes into a higher state of, let's say, energy. Yes, that once it goes to a higher state of energy, we say this atom is, or let's say this atom, let's say it is. Or let's say this electron is excited, yeah? But then after that, what happens, because it's not going to stay there, it's just not stable there, it is going to come back, yeah? But while it is coming back, of course, it is going to release the energy that it gained, or the energy that it absorbed. That is called spontaneous emission here. And then, of course, after that, we have stimulated emission. What do we mean by stimulated emission? It's almost like you're encouraging that, let's say, atom or that electron, let's say, to give out, let's say that atom to give out, let's say, a specific or sort of wavelength here, and or you can call it a light. That is basically called stimulated emission. Normally they don't do that, but we stimulate them, yeah? We encourage them, we make them do that. That is called stimulated emission. And of course, we'll talk about this one more once we talk about the work of a laser here. So, but remember, what are the three main processes of laser light production? You can say absorption, and then after that, spontaneous emission, you can say, and then stimulated emission. These are the three main fundamental, you can say, processes of, or in laser light production here. So one of the Zhyar questions that we have says, a laser, all right, it is a device that converts what? Converts chemical energy to electrical, thermal to electrical, electrical energy or light energy or chemical to monochromatic coherent light wave, or electrical energy, light energy, or chemical energy to polychromatic. Poly, we said, it means a bunch, yeah? Like a bunch of colors of light wave, or it's not a single color, yeah? So what would be the answer in this case? Clearly it is not A or B, so it is either C or D, yeah? So which one would you choose? Well, then it is C, because it changes or converts all that electrical or light energy or chemical energy into monochromatic, a single wavelength color, you can say, yet coherent light waves. That'll be for lasers here. Okay, now we can talk about the basic operation of a laser here. So what are the basic operations of lasers here, or how do lasers work? Now, previously we've said that these lasers, they have an active medium, yeah? This active medium, let's say, we said it could be a solid, it could be a liquid, or it could be a gas here. So this is basically, let's say, inside the laser here. So we have to give the type of energy or the energy into that active medium, which could be light energy, could be electrical energy, or it could be even chemical energy. Once you're giving this energy to that active medium, of course, this active medium contains a lot of particles, a lot of atoms here. So these atoms, or let's say the electrons of these atoms, once they absorb the energy, they go into a higher state of energy. So that is basically, now they're excited here. Okay, so once they are excited, of course, we can say that'll be the second step here, which is excitation. Let me go through the steps here as well. Maybe later on I'll draw a diagram for you as well. So energy addition, high energy light, electrical or chemical energy is added to the active medium. That is the first step, yeah? Okay, so we can say once energy is added, let's say, to the active medium, of course, electrons will be, or you can say atoms of electrons of that, let's say of atoms, of course, will be excited into, let's say this is a ground state or whatever. That is whatever the state of the electrons are, let's say. Once they absorb energy here, of course, these electrons now will go to a higher state of energy here. But of course, they are not balanced here. So soon after, you'll see that these electrons will come, would fall down to, or will go down to, let's say, the lower energy. Along the way, of course, they release the, let's say, a light energy here, you can say. Okay, and then along the way here. So this is basically the process of this one absorbing the energy and going to a higher state. That is basically called excitation here. Okay, so let me stop, let's say, on the this stage right there. I think we have this one here. So that is basically what we have. I think I'll have to redraw this one now. So that is, let's say, one atom after it gains, or let's say absorbs energy, of course, is going to go to a higher state. That is basically, it is excited now, but it is not stable here. So after that, it is going to go down. Along the way, going down, of course, it will release the energy that has gained here. So this is the energy that becomes a laser light, but that is not the only thing. Remember, this energy, of course, is going to be this light, of course, it will stimulate, encourage, or you can say force other particles to give out the same light, and then after that this light will be amplified. Then after that the light can go out and become a laser light, the one that we see. So going back to the steps, we said the first step is energy addition. We added energy to the laser, yeah? This type of energy could be light, could be electrical, could be chemical, that is added to the active medium, which can be a liquid or solid or gas. Okay, the second part is excitation. We said atoms in the active medium absorb this energy and are excited to a higher state of energy. That is pretty obvious, and I believe all of you know this one. What about the third stage in here? We can say the third one is energy release. So what happens when that, for example, electron is over there, yeah? It is not going to stay in the excited state forever, so it is going to, let's say, go down to let's say, original energy, let's say, state. Along the way, or once they are falling or going down, they release the energy that they have gained, requiring, or let's say, acquiring stability here. So they have to get rid of the energy that they have gained, and that is basically the light energy, or you can say the laser light here. But then that is basically called energy release, yeah? So excited atoms release excess, the extra energy, as an electromagnetic radiation when returning to their lower energy state, you can say. And then the next one is, which is also very important, stimulated emission. Now that is one of the key points in making lasers here. This stimulated emission here, when this light, for example, that is emitted from this one here, it is going to, let's say this light is going to, let's say, encounter other electrons here. Once this light is encountering other electrons here, now this is basically, after this light, for example, it is encountering this, let's say, electron here, it makes this electron to, let's say, release two light waves here. These two light waves are basically exactly the same, or you can say coherent here. So same phase difference and all that here. So these two light here, if I do this correctly here, so these two are exactly the same. Let me just make this one accurate enough so that you know what it is. So let's say this is something this, okay? So these two light waves here, all right, remember we had one, now we have two, okay? You might say, well, where does it come from? It might violate the law of conservation of energy. We'll get to that question too. Okay, so when this light, for example, encounters this electron here, it makes this electron, for example, that is the first light wave, that is what is gained, and now what is released here. And then, but this electron is going to release another light wave, or you can say another electromagnetic wave here, which is the same, you can say it has the same wavelength and phase difference with the first light wave here. This is what is called stimulated emission, because you're stimulating, you're encouraging, you're forcing this electron here, let's say, to emit or to give out another electromagnetic wave, let's say, that is exactly the same as this one in terms of the wavelength, in terms of the frequency, and also in terms of the phase difference as well. That is what is called stimulated emission. So when a light of a certain wavelength, it has a certain wavelength, encounters with an excited atom, by the way, yeah? So these atoms, you can say, are the excited ones here, yeah? So that is what happens. You can say now these light, or light from this, of course, will encounter with this one here. So if each light encounters with this one here, so this one, of course, will give out two here. So let's say something like this. These are, let's say, same phase difference and all that. So of course, we'll have another two there. I should have done it in the same wavelength as well. Okay, how about we draw this one properly here. So that was the first one, let's say. Now, these are, of course, we have different wavelength here. So one wavelength goes into encounters with this. Now, of course, we will get two, let's say, light waves here. That is one, let's say, there is this one, two here. So that is two here. Now, of course, now, one light wave can encounter with this one here. So, of course, we will get two here. Okay, so this process is basically what is called stimulated emission here. And, of course, one here as well, it encounters with this one here. So we will get two light waves here. So let's say two light waves. Let's make this one a little bit proper. Okay, so that is this, and here's what we have. So this is basically each one of these lights, for example, where these magnetic waves encounter one electron or one excited atom, by the way, we will have two waves here. So imagine this, if we have two, for example, one get two here, and then one get two here. So of course, eventually we get a bunch of light waves moving back and forth. Why back and forth? Because of course we have, let's say, mirrors. Okay, these mirrors allow, for example, these light waves to go back and forth until we get, for example, high intense wave light. Then one of the mirrors partially transparent, then allows the light to go through. But let me not get ahead of that. So we are at stimulated emission. So what was stimulated emission? Of course, when electromagnetic wave encounters one of these excited atoms of a certain wavelength, of course, we'll get, let's say, or this atom, of course, that releases two electromagnetic waves of the same wavelength, same phase difference, you can say, or you can say these two will be coherent and is identical to the light that encountered with the electron here. Okay, then after that we have light amplification. Now I think that is obvious. Light amplification, making it, amplifying it, yeah, making it bigger here. How can we do that? We'll say, but I think I did not go through the whole thing. Actually I did. Okay, so the initial light wave causes, so this light amplification, we can say the initial light wave causes other energized atoms to release more light waves. So we can say, of course, one electron releasing, for example, the electromagnetic wave, then becomes 2, then becomes 4, then becomes, let's say, 8, let's say, then becomes 16, and like it increases more and more and more. This process is called amplification here. And then after that, or something more than that, after amplifying this, we have mirrors here. So of course we have a mirror system. Mirrors to both ends of the tube reflect light back and forth, and of course releasing, let's say, or increasing the intensity of the light. And then eventually we have the output. We can say one of the mirrors is partially transparent, and of course once we have enough light intensity, then the light would finally can come out or go out of the laser, and then we can eventually see the laser light as the light that we see here. So, and of course, that would be the basic process of laser light. And of course, this is what we have. Now, let me give you a simple version of, let's say, my own explanation for this one here. So first of all, we have, let's say, atoms here, or active medium. Of course, inside the active medium, there are atoms there. And of course, once we, for example, give energy to these atoms here, like we said, whether it is light energy, electrical, or chemical, these electrons will be excited. They go to a higher energy level. And of course, once they come back here, for example, they're not stable here. Once they try to come back, along the way, they are releasing, let's say, their energy. Now, this energy, of course, is going to strike other, let's say, atoms that are excited already. So let's say these waves here, and of course, one wave will go into or encounter the atom, and of course, we get two waves back here. Okay, these waves are basically, you can say, same or identical to the wave that struck the electron here, same wavelength and all that. So of course, we get a bunch of, you can say, electromagnetic radiation. And this process is called stimulated emission here. Okay, and now this would be for that. These are, by the way, these are all inside the laser light here. So this is basically the laser, we can say, and there is inside the laser, there is an active medium here. These are basically, this thing happens all the way there. And then this process of one light encountering with one electron here and getting two, that is basically called amplification here. And then at the two ends of a laser light, of course, what do we have? We have mirrors here. What is the purpose of this mirror? It allows these laser lights to go back and forth until we have enough intensity. Then one of these lasers, of course, is partially, okay, transparent, then allows the laser light to go out as a bunch of, for example, waves here. These are all coherent, same wavelength and phase difference and all that. And this is basically the laser light that we see, of course. And this laser light, you can say, it can be later on used for many purposes. Okay, so now this is basically what we have. So we have stimulated emission, you can say excitation, stimulated, let's say, emission, or spontaneous emission. We have, by the way, spontaneous emission, that would be this. Stimulated emission, that would be after one encounters an electron, let's say, then two electromagnetic waves identical to this come out, you can say. That is basically, you can say, stimulated emission. Then amplifying, when it goes or keeps back and forth, let's say, then one encounters, for example, one wave makes two waves makes four waves makes 8 waves, and this process continues. That is basically called amplification, yeah? And then after that, we have basically, we talked about the mirror system, okay? This mirror allows the light to go back and forth until we have enough intensity or strong beam, and then one of the mirrors is partially transparent, allow the light to go out. That is becoming or becomes the output for a laser. And of course, you can see what happens here. This is the active medium, you can say. The atom's an active medium. Once you give them energy, they'll be excited. You can see here one, let's say, electromagnetic radiation. After they, for example, go to an excited atom, they fall or they come back to the same energy level. So they will release energy, as you can see. This energy that is released is going to encounter, let's say, encounter with one of the atoms or one of the, let's say, electrons here. Then, of course, one, or you can see here, one of these, of course, becomes two here. That is, you can call it spontaneous, stimulated emission here. As you can see, one goes into the atom, and of course, two comes out. That is called stimulated emission. Then this process continues. You can see back and forth, back and forth. These are basically the mirrors. Once we have a nice enough high, let's say, intensity beam of light or laser light, then of course one of the mirror allow the light to go out of the laser, and this is the light that you see here. Okay, take a look at these questions real quick. Says, what is the property of a laser light called that causes coherent light to be emitted here? This is one of the questions here, which is very important. So look again. It says, what property of a laser called that causes coherent? Yeah. So which property causes this coherent in laser light? Is it different intensity? Is it light amplification? Is it monochromaticity, or is it simulated emission? We said the property that makes laser light to be coherent, and of course it is monochromaticity, you can say. It has, all this has a single wavelength, you can say. All these are together here, yeah? So none of the other ones. So the correct option is going to be C here. Which of the following is not an essential component of a laser? That is also another part which is very important. Partially transparent mirror, that is part of it. A fully reflecting mirror, that is part of it. A converging lens, we haven't heard about that. What about the last one here? Says an active medium. So this part of the laser. So the only option that is not part of the laser is a converging lens, but because we don't use any converging lenses for lasers here. We just have mirrors, you can say. On a laser source, the energy is called what? What is it called? Is it mirror, active medium? On a laser source, okay, or has to be what? Okay, the energy is added to, okay, on a laser source, the energy is added to which part of the laser? Is it added to the mirror? Is it added to the active medium, or partially transparent mirror, or light waves here? Of course, the energy is added to the active medium here. But there is one question I haven't answered. We have it later on, of course, you will see that. When we said one light wave, if I go back to this, you can see one electromagnetic radiation, all right, encounters with the atom, let's say, okay, or the electron, if you want to call it. So then, as a result of this, we get two. Where does the other electromagnetic radiation comes from? Doesn't that violate the law of conservation of energy? Like, where do we get? It's almost like you give 1 joule to, let's say, an object, and then it gives you 2 joules back. Isn't that violating the law of conservation of energy? We'll say no. Why? Because these electrons are already excited. Why? Because you gave energy. These are basically, they gained energy because these are active or part of the active medium. So when you first gave energy to the active medium, they absorbed energy. And now they're excited. So once you make them this one, of course, they'll release enough identical to this one, and also they will release enough, or you can say another electromagnetic, let's say, wave. That is because they absorbed energy from the active medium, you can say, or once they were, or the energy is given to the active medium. So the answer is no. Let me make it simple, right? It does not violate the conservation of energy or the law of conservation of energy, because these electrons did not give out an electromagnetic radiation out of nothing. The energy or the extra energy they gave out, they have gained once energy were given to the active medium. I hope that makes it clear to you guys. Okay, moving on to these questions. These are also very, very easy. I hope you guys do them. Or at least know them. The last one says, which of the following is essential component of a laser? So the components that are essential: partially transparent mirror, fully reflecting mirror, and active medium, or all of them. And of course, these are all essential, important parts of a laser. Okay, applications of lasers. Now we have lasers, and we have another type of lasers called maser. Yeah. So what is the difference between the two? We're going to clarify. And of course, we can say laser uses as well. Okay, so what are lasers? Lasers come in different types with wavelength. This is what basically lasers or the light of lasers range from. Okay, they can have, let's say, wavelength far from infrared all the way to X-ray. Do you remember the electromagnetic, let's say, spectrum? We have radio, micro, infrared, visible, ultraviolet, and of course we have X-ray and gamma ray. Yeah? So ranging from infrared all the way to X-ray, of course, we can have lasers. Yeah, and based on these, of course, wavelength, some of them you can see that does not have a low, let's say, high energy, but some others like X-ray lasers, of course, they're very powerful. They have a lot of energy. You can say some lasers can even be used for cutting metals. Okay, so imagine how powerful those lasers are. Okay, now we have another type, okay, of, you can say, not a laser, we call them masers, yeah? So what are masers here? Now, as, for example, do you remember how we were defining lasers? We said light amplification by stimulated emission of radiation, correct? Now, if it is masers, it is the same as, or you can say, same principle as lasers, but what it does is, instead of using light, it uses microwaves, yeah? So microwave amplification stimulated by emission of radiations, you can say. Okay, so masers, again, instead of using light, which is visible, you can say, or the colors of that, they are using microwaves, yeah? So they're still using, let's say, infrared, electromagnetic waves, but which, let's say, which wave specifically, they are using microwaves here. So microwave amplification stimulated by emission of radiation, you can say. So always remember this. If it is laser, that is light. If it is maser, they might tell you what region do masers work in. Remember, maser, microwave. So their region is microwave region. That is the field or the region they work in. What are some applications of lasers? Lasers can be used in everyday items or everyday, let's say, items. It could be industrial processes and specialized medical treatments as well, which we're going to talk about them right here. Okay, now there is another question, says, in the range of which of the following waves are maser working? So once again, maser, all right, microwave, don't forget, yeah? Is it gamma, X-ray, ultraviolet, or micro? It is micro, so maser, micro. Okay, next. Says lasers are used to determine distance with great precision here. Didn't we say lasers are very focused, very intense, let's say? So of course, they don't spread a lot, let's say, in terms of spreading, let's say. So of course we can use them or they can be used to measure distance with great precision. So what are some uses here? We can say because of their narrow beam, laser light emerges as narrow, so well collimated beam with minimal spreading here over distances. So they don't spread a lot, yeah? You can, of course, they can go kilometers with spreading maybe with, let's say, within millimeters, let's say. So they don't spread that much, yeah? So unlike light from a bulb where you can say reflectors, that spread a lot, let's say. So lasers, they don't spread a lot. You can see here, of course, even though they can travel so far without spreading much to mention. What about directionality? We said that all lasers, or laser lights, basically, they travel in the same direction. It's not like they travel in different directions. They're all coherent. They travel in the same direction, making lasers ideal for measuring long distances here. So how do we use long distances, or how do we use them? Of course, we can use them for so many purposes. Now they use lasers, for example, to measure the distance very precisely because they don't spread much, yeah? That'll be one of the reasons why. Another reason is they are unidirectional, you can say, or they don't spread much, let's say. Okay, and of course, by the way, regarding the distance, we have velocity equal to distance over the time, yeah? But since lasers are light, so we'll use speed of light for their velocity, which is 3 times 10 to the power 8. And then, of course, giving the time, how long it takes them to come back, we can measure the time, the distance. Okay, now lasers can also be used in astronomical use, yeah? So normally astronomers use lasers to measure the Earth to Moon distance. How do they do that? Okay, imagine if we could, for example, let's say have a mirror on the, let's say, surface of the Moon. You can direct a beam of laser onto the surface of the Moon, and of course you can time it, okay, and then the laser will be reflected back to the Earth, knowing, right, or knowing the time it took to go and come back, we have the velocity of the laser light, which is the speed of light. Then of course we can measure the distance between the Earth and the Moon. Okay, that is basically, we can say, what astronomers use normally. Okay, so they direct a pulse of, let's say, a pulse at reflectors on the Moon's surface, and of course timing the return, they can tell the distance. And then one more use is, let's say, geological use. Because lasers, you can say, are very precise, so geologists, you can say, use lasers to monitor small changes in the Earth's crust height. So because, you know, like the crust, let's say the surface beneath, let's say, or just the floor, let's say, you can call it crust, yeah? In geography, you can call it. So this crust is moving, of course, due to a lot of reasons. Plate tectonics could be they're moving as well, yeah? So to monitor the changes, what happens, sometimes get thicker, sometimes get thinner, sometimes they drift apart and all that. We can use lasers because they are, they have very, or you can say they have great precision. So we can use lasers to monitor the changes to the crust. It can, of course, it can tell us, or it can measure changes even with few centimeters, that is, to the crust. Okay, now some other uses of lasers, but this time in medicine here. So what are some applications of lasers in medicine? The first thing, nowadays, a lot of people use lasers. Yeah? It could be for hair removal, facial, hydrofacial, whatever, yeah? So for a lot of purposes, yeah? And of course, some of them are necessary, for example. Some of them are just for, let's say, I don't know, some for accessories, for decoration, whatever you can call it. But let's go through some of the uses that lasers are used in medical, or you can say medical applications. The first one is, we can say lasers are used in medicine or medical procedure because, let's say, because specific body tissues absorb different wavelengths of laser light. Yeah? So of course we have body tissues. If each body tissue is different, for example, than another one, each one of these, of course, would have or would work under, let's say, a specific wavelength. That is basically how it is. Then each one of them, if you use, for example, or direct a laser light that has a specific wavelength to that body tissue, of course, you can cut it, let's say, you can remove it, you can heal it. It depends on what the process you're doing. Yeah, why can we do that? Because every body tissue has a different wavelength, or you can say it can absorb different laser wavelength, if that is what you like to call. Okay, that is the first one. Second, lasers can lighten or remove scars and birthmarks. So for example, let's say, God forbid, something happens to you and you are left with, or you got some scars, yeah? So could be on your face, could be, for example, on your hand, or let's say on body parts, let's say. This laser, right, can either remove the scar completely, or if not remove it completely, at least you can make it lighter. Like, for example, it makes it less obvious because these lasers have the ability to, let's say, remove or make it lighter here. Okay, so it could be a birthmark, let's say, without affecting the surrounding tissues. This is one of the benefits of lasers. So, for example, you can target a specific area that is this small without affecting, let's say, the surrounding tissue. As scar tissues respond to specific laser lights, that is obvious. Now, the third one, we can say high-intensity infrared light from the carbon dioxide lasers, okay, which have a wavelength of about 10 micrometer, can vaporize water, and if they can vaporize water, allowing these, of course, to cut through muscle tissues or muscle tissue by heating and evaporating, let's say, the water in cells here. So for example, you're trying to do something. Laser, let's say wavelength or laser light have the ability to evaporate the water in that tissue. They can penetrate through that tissue. They can kill that cell, let's say, or they can cut it, for example. Yeah. So this is what lasers can do, for example. So that is why, that is because of their high intensity. They can be used, for example, as a regular scissor instead of a regular or ordinary scissor. Okay, now 4 says laser energy also coagulates blood in newly opened blood vessels. So let's say there is a wound inside the body part, and of course, because if it is, let's say, location, we might, or let's say the surgeons might not be able to penetrate into that body tissue, or it's not easy to get into that part and stop the bleeding. So what is the best solution to do that? Direct a laser or a beam of laser, and that beam of laser, of course, it can stop the bleeding here. Okay, so this is what another use of lasers. So lasers can be used to coagulate blood or stop blood in newly opened blood vessels, reducing blood loss and decreasing the infection of risk as well. Another application of lasers is this, laser beam can be trapped into optical fibers, let's say in endoscopes, of course, enabling internal procedures such as stopping internal bleeding, we said, removing tumors without massive surgery as well. So this is basically another application of that. They can use lasers as scissors without needing, for example, to cut open, let's say, your body tissues too much. Lasers can do that by directing that laser, for example, into an optical fiber endoscope. Okay. Another use of laser is this: lasers can treat tissues unreachable by conventional methods. I think we've all sort of mentioned that one, but this is just to emphasize on that. Specific wavelength can pass through the cornea and lenses, let's say, to treat retinal lesion here. For example, now we have LASIK, let's say, lasers, or let's say eye surgeries using lasers. It's called LASIK, one of them, or at least one of the type here. And of course, you cannot, let's say, just cut open an eye, let's say, and do something or fix something, let's say, at the back of the retina, let's say, or the back of the eye, at the retina, let's say, or somewhere closer or further there. What is the best option to do that? Of course, we can use a, let's say, a laser light, and of course, it can do the job for us, let's say, without cutting open, let's say, the eye. But remember, not any type of laser. So you cannot, let's say, put or direct a laser beam, let's say, into somebody's eye, because that is super dangerous, and I don't recommend you to do that at all here. Because those lasers that are used for these purposes are specific. They don't have, let's say, high energy, but they are not that intense here. Those lasers that, of course, you have or you've used there, these are very powerful. You direct it to the eye of somebody, God forbid, you might just blind them. So these are not used to direct, or you're not allowed to direct it to anybody's eyes, not even a pet. Okay. And then another purposes, of course, lasers, another use of lasers, we can say lasers are used in eye surgery, such as, let's say, for glaucoma, by burning a tiny hole in the, let's say, in tissue to relieve the fluid pressure and prevent optic nerve damage and, of course, blindness as well. Sometimes there are, let's say, some fluids, let's say, combining or piling up, let's say, at some specific locations. This fluid combining or piling up, they might apply a lot of pressure, let's say, on that body tissue or a nerve, and of course, that causes a lot of damages here. So this fluid, let's say, must be, or this pressure must be depressurized so that you can keep the tissue, the nerve safe here. So you cannot, once again, it is perhaps you might not be able to do that with conventional tools, so laser would be one of the best options. You can direct a laser beam, right? You kind of like open a small opening, and of course this fluid would come out, let's say, and of course now there would be no pressure on that body tissue or that nerve, let's say. Then of course the person would be fine. Okay, and then that, of course, you can do that to save the person from blindness. Then another, let's say the last use for now is lasers can correct nearsightedness by flattening the central portion of the cornea with focused laser beam as well. One more time, for example, now we've mentioned LASIK surgery. So now lasers, of course, commonly used, let's say, to treat, let's say, nearsightedness. Nearsightedness, of course. And how do they do that? They flatten the central portion of the cornea, hoping, for example, so that the light will be, let's say, combining at the point or the position where it's supposed to be. And this is how they can use laser to correct the, let's say, the eyesightedness, if that is the correct one. Or you can say the sight. I think that's what it's called. Okay. Anyway, now we have one more question for now, and then perhaps we'll end this session. It says, give two examples in which the uniform direction of laser light is advantage, and also two more examples in which, or you can say two examples in which the high intensity of laser light is advantage. So these are two separate questions here. One of them gives two examples in which the uniform direction of laser is useful. Okay, so give two examples where the uniform beam of light is useful, and two other examples where the high intensity of the laser light is advantage. And of course, we've measured this, or we've mentioned this, that we said, like regarding the uniform direction of laser light, two examples for that, we said we can use that to measure the distance, yeah? For example, enables precise distance measurement, yeah? Because it is uniform, it doesn't spread, let's say, a lot. Another advantage is, for example, for eye surgeries here. So because it is so directional, so you can direct it into a point without affecting the surrounding tissues here. So we can say it is accurate targeting of specific eye areas without damaging the surrounding tissues here. And then two examples for high intensity of laser light, we can say cutting muscle tissues, because they have a lot of intensity, so they can cut through the muscle tissue without, let's say, damaging the surrounding cells, let's say. And another purpose, or you can say advantage or example for that is, we said coagulating blood vessel, stopping, let's say, a blood vessel from bleeding. That, of course, reduces blood loss and infection. And of course, we have two more examples. You can take a look at this too, and I'm sure that you know the answer to this too. Next time, inshallah, we'll start with the section review, and hoping, inshallah, we'll finish this, and so that we can start chapter 8, inshallah. Till then, keep practicing, and I'll see you soon. Assalamu alaikum wa rahmatullah.